And again, we'll go to full screen mode. Okay, this is the third one. This is we're actually getting into the Simpson strong frame introduction, so you guys see what it is, what makes it so special, what some of the detailing, and what some of the components that makes up the connection. So outline, basically walk you through how this was kind of developed, what was behind it, why did we develop this way, or how did this connection come about, and then review some of the development and show you some of the testing, how performance of it, and then the catalog solutions. You guys won't have to deal with it, but it's good to know what we're offering. So that's outside of it, then that's what you're pretty much dealing with. And then review of this. So these are the, when I mentioned the Northridge earthquake before, this one is actually from the field. They saw what happened. So here's a fracture. This was the one that we duplicated in the laboratory. So I tested this one, so we duplicate this in the laboratory. So this is actually what happened during Northridge when they pull out. See this here? It all started at that stress concentrator right here at the where the backup bar removal. Remember I talked about that, and then you have to put it fill it now the requirement. So before there's no requirement, they just left it in place. That's where it started. Also there's some other stuff as well, but a lot of quality control issues. Concentrating all the forces in maybe one frame before. So it's a lot of things that led to it, but they ever since then FEMA came out the 358, and now the AISC took over that and starting to put some of the requirements that perform well into their documents, and so that the engineers could choose from. Here is the RBS. When we talk about the reduced beam section, that's what a failure, not a failure, but that's what they're intended to do, right? The column connection, everything stays good, and then but the failure. Just imagine, can you replace it after an earthquake? So if that's what earthquake did to it, what do you need to do to replace it? Well, definitely you have to take out the whole beam. So that beam is gone. You can't really reuse it anymore. Right. So this was another test that I did in school. So this is 2%, 5%. So that's what the 4%. That's the 4% drift, or the 0.04 radian we're talking about. So this is at 4, and this is at 5 for the different specimens. That's what they look like. And so when the code says you need to meet this requirement, at that point, that's how how bad the beam is at that point. So it's very damaged at that 0.04 radian. So it's very bad at that point. This is the slotted web. So their failure modes are here. Here's the slot. Here's a slot. So this was actually a testing that they've done, but the failure mode, even though they're able to get the 0.04, but the failure mode, the whole beam is gone. You see this? I mean, that's all fractured through. You can't reuse that beam anymore. So you have to basically replace it. Okay. Another concept is to reduce the web. So instead of cutting the flange out on top and bottom, they cut out the web. Okay. Again, when you cut it out, at the end you're starting to tear at the corner. So again, the beam is, you have to replace the beam. End plate, and also another one that's been to satisfy the SMF. So at the end, what does it look like? Oh, this is local flange buckling, local flange buckling. So again, you can't really use that beam anymore. It's done. This is the free flange one. I say it's pretty much the same as the one we saw. Again, here this one's even worse. Not just that the beam, when it failed, actually took out part of the column, so cracked the column through. This is pretty bad. So we don't want to see that happen. But when it did it, I don't think this is a pre-qualified one in FEMA 358. This one is not pre-qualified, but it was in the 350. So they have not qualified this one as a special yet. Cover plate, I believe that's one of them. Again, the idea is you either weaken the beam, so you cut something out, you concentrate all your demand on the beam, or you don't want the connection to fail, you make this connection stronger, but the idea is still try to form the hinge in the beam. So either cut it out, or this one is leave it. So, but if you leave it, you would have to reinforce the connection. So what they did here is weld the top plate, bottom plate, and here's what the beam at certain 4 inches, 3 cycles. That's very, very damaged after testing. This was the Kaiser bolted bracket. This one is, again, you see deformation. I call it, this is the strengthen the connection. So make the connection stronger, but the beam is what's going to fail. Instead of cutting the beam, weaken the beam, and make the beam fail. Either way, the beam still failed at the end, or no, it still does what it does. This one, the weld starting to tear here, the weld starting to tear. So that's a failure mode for the Kaiser bolted bracket. Another one to retrofit or to strengthen the connection is, again, you put a hunch here. You make the connection so much stronger, because you don't. Everyone is worried about the weld fracturing here, like Northridge, right? So you force everything out to the beam. So you can see how bad the beam it is, So you can't use it. This is only at 3%, not 4%, 3%, and that's how much it's doing what it's supposed to do. Okay, the occupants could walk out after the building, but now, what happens to the building? You're gonna have to demo it and replace these beams. Okay, so the concept is, so this was tested in 2005. Another one is, again, to reinforce the connection. Doesn't matter how you do it. This one they put the rib. If they force the beam to yield, again, the beam's yielding, but you can see at the end that connection here is tearing up, and it did what it does, but you can't keep the beam or the building. Imagine after that another earthquake comes by. You don't have anything at that time. This was our side plate, a competitor. They strengthened the connection, but they again still forced the failure in the beam. So here's the testing photo. All the very buckling were a lot, and then they show some of the FEA numbers here. But just to show, beam is failing. Folded flange plate. This is another pre-qualified one. This is at 6%, so we're a lot more than what's required. But the failure mode is at the bolt tearing the flange on the bottom, so that's what's tearing. You see, you wouldn't be able to use the beam again. Okay, and also, this is what lateral torsional buckling is. You see the beam? It's out of plane, like you say, at that point. This is 6%. That beam is curving. This one is curving at 5%. You can see it. So here's the actual test result. You see the different failure modes. So, summary. I mean, basically, like I say, there are 2 types of traditional SMF connections. You're going to weaken, actually the EEK, weaken the beam, or stiffen the connection. For all of them, the beam is used to dissipate energy. A plastic hinge forming in the beam. That's what people call plastic hinges. Actually, when it twists off, develop the beam, that's called plastic hinge. They're forming in the beam. It's doing what it's supposed to do. Yes, that's doing what it's supposed to do. But if you look at how much damage at the end, what can you do to move back into the building? There's a lot to do. They probably cannot use the building for a while. So the beam and column panel zones can also dissipate energy. We saw the column panel zone. I'll show you a little bit more in this one later. But you do see some of them is whitewash starting to flake on the panel zone. And what we mean by the panel zone is actually this area. This area is called the beam to column panel zone. So it's yielding already. But this is very ductile. Yielding in the panel zone is very ductile. So that's the beam and the column panel zone also dissipate energy. All beams will need to be replaced after a major earthquake. I mean, you can see that's what's going to happen. So in order to get the plastic hinge to form in the beam, they'll need to be braced to prevent lateral torsional buckling. Yep. So that to prevent that mode, and typically you see that's the bracing. Beam. That's what we mean by beam bracing. Is these bracing? The top is being braced by the floor. So they still need to brace the bottom. So they need to brace the top and bottom. The top is done through connecting to another beam, this they need to kick back.
So if the roof beam of the hanger on steel beam, so we consider it's a brace.
Yeah, this will address it.
Yeah.
When you're doing bracing, not only how much they tell you how much force that brace have to be designed for, but the brace also have to have certain stiffness.
Yeah.
So stiffness is very hard to meet.
Yeah.
That because of the wood, it's not you can't get the stiffness a lot of times. So beam bracing is addressed in the 341 code, the seismic code, and that's what we're talking about. Steel beam sections are meant to be permanently deformed in a typical SMF connection, like the pictures I show you already. Okay, like these more pictures, this one's under fire, this one's under some other condition. What can you do after an earthquake? Not much, no, especially where you're welded all together. So seismic bracing, it's spelled out in the 9.8 of the 30405. This is the length of the bracing. So LB is in RY, and then EY and FY. So basically, that's how long, how often you have to put the brace. Okay, so the LB, this is you put it in is the design equation. The E and FY doesn't really change. E is the 2900. Is the material properties. FY is material property. The RY that depends on the shape. So if you have a bigger beam, shallower beam, so that would change. So each beam would have a different brace length. They would need to brace it. Okay, so that's bracing of the beam. Also, in addition, you should place a brace at concentrated loads. So if you have a beam and you have concentrated on the middle, they say you need to brace it at the concentrated load. Okay. In addition to that, here's the requirement for the strength, the PU or the P brace. Here's the brace force. So MU divided H naught, 6% of it, and that's the force. However, the required stiffness is spelled out somewhere else. So when you do the bracing, beam bracing is not that easy to do because you have not only the stiffness, the strength you have to meet, but you can't, according to this one, it's really depends on the shape you use. You have to brace it. If they tell you to brace at 6 feet, and you're 6 feet, most people will change the shape. Okay, I want to change it to bigger section so that it's not twist easily. Then you could go further. Okay, maybe I'll provide it every 12 feet. The one thing about our side plate connection, those moment frames are anything greater than 12 feet, they will start needing bracing. Anything less than that, they probably don't need bracing because of that equation right there. So that just tells you. Or unless your connection is tested without the bracing. So beam bracing problem, we could see here's the stiffness. I'm not going to go through it. They tell you some stiffness. So if you kick it back, you have a floor, you have a brace. What stiffness are you getting here? So that is the problem for that. So knowing that in mind, Steve and I didn't develop it, so it's whoever developed this before. So, okay, what's the best thing to address this solution? Beam bracing. Okay, first is all, well, what if you don't form the plastic hinge in the beam? That's the first thing. We're not going to form the plastic hinge in the beam. Okay, we're going to concentrate everything on the length that's outside of the beam. So that's what it is. Provide a stable plasticity via some kind of proprietary connection, a yielding link on top and bottom of the beam. So now limit the strength of the connection so all the members, beam, columns, and other connection elements remain nominally elastic. This is the capacity design approach. Very similar when you're doing concrete design as well. Once you do a plastic hinge, then you do everything stronger than that connection. And that's basically the capacity design is you have a weak link, you design your earthquake and everything else, make sure the weak link is okay to satisfy the basic earthquake loads. But when a major one hits, that's going to be damaged. But the rest of your structure is going to remain the same because you have that dedicated fuse per se that's going to take out all the energy. So our concept is links absorb all the energy. links are the only yielding elements, pretty much. A beam and column are designed to remain elastic plastic when you're in curves, so mostly in the elastic range, and no beam bracing. So that's the concept, is what we're trying to meet and what we're trying to do. Okay, and also because it's bolted, you could, instead of having to replace the whole beam, take out the whole beam in an earthquake, you see all the damages, warping. All you have to do is just take out the link, top and bottom, put another link in, and you're good to go. So that is the concept. Okay, few bolted connections only. We're bolting it so it's easier to replace. That is our connection. You've seen it many times again, yielding, close up, and I'll go through. Here are some of the concepts of the connection. This is the first generation, so it's nothing like what it looks like right now. Before, actually, we welded a plate on the bottom, and then with a cover that to basically prevent it from buckling as well, and connection. So this is the first generation. Second generation, there's a rod that's yielding within the box. So remember, like column or concrete or steel, tension is very good, except concrete, right? But when you push it, you're gonna buckle. So this is what's trying to prevent from buckling. So it will perform both, in tension and compression. This is the final generation of the connection, and I'll show some slides of each part, what it does. Essentially, here is the link that's sitting there. This is the T one. We bolt it to the beam, we bolt it to the column, and there's some bolts, the plate on top, to prevent it from buckling. So here's a closer look at what's the connection. So the first step is the beam and the column. We have some holes here, some holes here. All these are standard size holes. These holes we tested to be a little bigger, so we could have tolerance for during erection. These ones also tested bigger, but for our stock frames, we actually slotted these holes too, so we could have the tolerance for the W shapes. The W shape, when they come off the steel mill, you could get plus or minus 1/4 inch. So the depth could vary by that much. So if your height is fixed, then you might not be able to fit in the beam. So the next step is we have a shear tap, and note that the shear tap is slotted on top and bottom. Slotted means that kind of oval, and then the middle one is a circular hole. So we slot the top and bottom. What that does is, okay, if you look at it now, when you're turning the whole thing, you're able to turn on the top because it's not bearing on anything. You're able to turn on the bottom because it's not bearing on anything. You're just pivoting around the center bolt. Pivoting around the center bolt. Next one is you add the link to it, the top and bottom link. That's what we have. Okay, we put some spacers here, so when we put the plate, it won't buckle. And also, what this does, there's a gap between the link and the spacer plate. We call to be 1/8 of an inch. What that does is when your compression, the steel and compression, they tend to grow out, right? Poisson's effect. When you push on it, the steel is going to expand in all directions. When you push on it, it's going to neck down. So we need to provide a gap in either side. Then put the plate. Because they tend to expand, we don't want the plate to be too tight either on the top. So what we do is these bolts are here are snug tight. And I go to different definitions of the bolt tightening with you later. So that's basically the connection. I didn't show the stiffener plate here, or the stiffener plate here, or continuity plate in the column, but that's essentially what it is. So we bolt this together. So what you see here, without the bolts here, is how we ship it out. With the nailers, with the connection, everything bolted together, we ship it out to the site. So the engineer, the contractor, all they have to do is bolt these in the field and bolt these in the field. So those are the remaining bolts they do in the field.
So you don't have much tolerance there for your columns to be.
In this one, we don't. In our actual ones, they slot it. in the column. We have
Oh.
slotted holes. These holes are like another 16-inch over. So not a problem, especially the ones we put together. It's just plenty of tolerance on that. We look into that quite a bit. So that's the basically our connection. That's the connection. The plate here, the BRP plate, is for resisting buckling. The neck down is mostly for all the energy dissipation. So, and then the shear tabs is slotted top and bottom so they could rotate. Testing. How did we get to this test? Those are the final ones. We actually have a light, intermediate, and heavy. That's what we did during testing. So for the light, if you look at the length, it's very, very thin. I wouldn't say compared. Half and a half is as thick as the heavy. So we had a 1/2 inch, 3/4 inch, 1/4 inch, 3/4, and half. All the geometry is pretty much similar. This one's longer, and then the column and beam sections are different. This one's very small. So you could tell here, W18. That's why we limited to those beam depth and column depth, because we tested it that back then. So heaviest is, instead of putting a weight next to it, 18 for the column, flipped it, 16 for the beam here.
Why is the length? Why is it tied to the beam? You got the capacity of the link by itself, right?
Well, when we design the beam has to be designed for that maximum load.
Okay.
So yeah, the smaller beams might not have the axial capacity or bending capacity for that. So that's what we have. So the testing here is I think you've seen the video. That I had the video on the folder, but I'm not sure I have it here or drag it over. I'll show you later. But essentially, we did test a full frame without any bracing. We just basically, here's the actuator to push the top and bottom. So the frame goes like that, back and forward. I do have some pictures show what it is. Because the capacity of the frame is more than what the actuator could do, we only test the connection on one side only. The other side is the pin connection. Pin connection, pin, moment connection here. That's the testing. Okay, the first test, the light test. Remember I told you how thin this thing was? It actually buckle and push out the BRP plate. Okay, see the performance? It's not very good when you have it so thin. Okay, the next one is the medium intermediate size one. We're getting very good loops. What I mean very good loops, very full loops, the ones you saw. This type versus this type, that's better. The area of what's enclosing is the amount of energy you're dissipating. So if you integrate the area or somehow get the area under the curve, that's how much energy you're dissipating compared to this one. So that's why when people say they always want full loops, is because the more energy you can dissipate from that system. Okay, so this one, we got the fracture where we want it. We want it to fail there. Okay, if it fails, that's where it fails. Okay, the third heavy test, decent loops. What wasn't anticipated was the fracture in the well. So if you look at this one, this was a fillet well. So that's what happened, actually fracture there. That's not a desirable behavior. Even though we got to the 4%. So 100 inches, that's 4 radians. We passed it according to requirement. However, that failure mode is not good. So what happens is we tested in 2012 when we try to put it into the 358 or get a 358 for approval. We were able to retest some things and then show them we don't have the non-ductile failure mode. So in this one, repeating with 3 again, we didn't do the 2 light ones. We only did the heavy one. Okay. So also we did some modification to the heavier ones. So first of all, to take care of the fracture, that well in the flange connection now is a CJP well. That's we're able to develop the plate capacity, a lot better well, a lot heavier duty well than what was there before. The second one is to prevent it from buckling, we're using a thicker plate. Okay, we didn't see the heavier one and the middle one buckle. It's only one is so thin when it started to buckle, it just we didn't want to be able to control it. So we thicken it as well, just for the sake of this test, and we got all the plate materials here. This is very impressive. You look at it, okay. This is just monotonic. Monotonic we're just pulling on it. We're not doing any cycling. This one is the column. Here's the beam. 100 inches. We were able to pull it to 9 inches. Okay. We stopped because the actuator strokes were limited. We didn't want to go out too much. So this is what's required, 4%. We were able to double that. That's what's required. And what's impressive is, you take everything out, look at the beam. No damages, no damages, no damages, because the links did not break on this one. Okay, so the intention is during a small earthquake or medium size, even large earthquake, the engineer is going to design how much that is for that earthquake. Okay, the test, they want to test it to the end to see what the failure mode is. It doesn't correspond to what the design low is, but if you see this one, you see there's like an inch difference. This is pulling steel, this is compressing steel. So there you could actually see it from the testing. Another one is after we tested heavy, so we were able to go to 4.5, 5 before. This one is we actually cyclic is we were able to fracture it where we want it. So if this does something happen, we could take the link, replace it, put another one in. Okay, so that's what happens when you look at it. Why did we see a little elongation here is, think about the arm with the moment arm. If this one fracture on the bottom, there's no moment arm here. So the next moment arm, next force is the center bolt. So it's the center bolt and the top one is providing the remaining force that's required. Okay, that's not a design. We're trying to design it to whatever low and size it to whatever low, but knowing the final failure mode is the important. So catalog review or preview, it hasn't come out yet, is what kind of beam and column sizes are we offering? What are some of the geometries, standard sizes versus custom sizes, engineering offering, our anchorage. I'll show you what that is. Basically, I have two types, MFSL, MFAB. I have a different presentation on design of these anchorages somewhere down the road. And then installation details we provide. And also, this catalog, we condense both the OMF and the SMF. So we also cover the OMF, standard, custom, two-story, custom installation details, one-story worksheets. But mainly what we'll be covering is just in here, for I'm going to go over with you guys, is just the top portion. I will not cover the OMF stuff. So, standard beam and columns. We only have 4 columns and 2 beams for our standard. And that's what you saw when I dropped down the Excel menu. We only have 2 beam sizes for us as standard. And that's what we offer. Geometry, definition. W1 is critical. That's the clear distance. So people wants to know the opening. H2 is not so critical because if you could fit it, then you could fit it. If you don't, they probably use a different column. But that's also there. Our software defines it a little differently. The software asks how much room you have for each column. So depends on how you guys want to set up your spreadsheet to get it. So what is the maximum size we could have for the column? That's what you're trying to ask for anyway. Okay, so the next one is the H1. That's the total distance, the height from the top of the concrete to the top of the double or fuel installed nailer. And then H3. H3 is the clear distance. So how much clear height you have, so people can walk underneath it. So naming legend, not so important to you guys right now because you probably won't be dealing with this. But we always have the SMF in front to indicate as SMF frame. We'll have to come up with some kind of naming scheme for it. We have like 2-bay or 2-story to see what kind of name that is. So we haven't thought about that yet. So maybe we'll start doing it. Maybe just project name, that would be okay. Or we need to put the beam and column sizes on the plans when you send it back to the engineer anyway. So we probably will not have a model name per se for those non-standard frames. All the column sections, I'll go to what A992 and what grade 50 mean later on. But here's the sections. Here are the maximum 16, 18. We cannot fit in a 2x8 wall, so we left limited to 16 on this one. Standard. Here's all the catalog offerings. So we go from 8 foot height to 20 foot wide, 8 foot to 24. So anything that's outside of what I just showed you is considered special. You guys might have to be involved, or they could just take my one-story spreadsheet. The engineers could just use that one, the 2 templates, and do it themselves. So it depends on what they want to do, because that they still need to generate the elevations and send it back to the engineer or the architect or contractor to review. Custom size, 1 bay, 1 story is the same thing, same terminology, everything is the same, so we get the same numbering, the naming, except that when we do the name, these are by the beam length and by the column height. So they could actually get it to, instead of to our standard sizes, we could actually get it to a 1/4 inch. So every 12.25 inch, 12.5 inch. So let them do whatever that's custom. The software will only take 1/4 inch increments. So I'll show you the software later when I install a new one there. But column shapes, bin shapes, all the same. We're not doing any custom or any shapes for these when we call custom frames. So connection to the anchorage, I'll show you a little bit later. Beam to column connection. The other picture shows a little better what needs to what needs to be done first. So this part is all done in the factory, and this bolting is in the field. This is important right now. Is depends on what column flange. You might have to specify the length of the bolt to make sure it's not too short, and that's why I drew it in there. So these bolts, make sure they're long enough to go through the column and the link, and with the washer and the bearing plate here. The bearing plate here, you see we have an elongated hole in the bottom too, and because you're elongating the hole, standard size washers you can't use it, so you have to use it. You use a heavy or bearing plate that's bigger. 2 types of anchorage, the MFSL and MFAB. And the difference between these two are basically we have a shear lug underneath here. We don't have anything in this one. Orders, don't worry about ordering. I'm going to basically how customers order. You guys will be helping out what to do when we're beyond the catalog and the software. You guys are here. This is when you know. This is what Tim's presentation. One branch engineer from 20 and 22 will be your point of contact. We'll be getting new licenses set for them as well, so they can review your work, and then you guys will look into purchasing SEP, and I'll give you I'll look into it and see what version of SEP you need to buy, and then engineering service hopefully will be ready to support them when they launch. So this probably launch is mostly 1 story, 1 bay, so it takes a while after launch to get to those custom ones.
When is the launch date?
January 7th. 2013. And then important to know the limitations. This is what we're trying to ask them to, if they see anything in the plan, these are the opportunities they could convert. So make sure it's the floor or steel corrugated panel with 1 inch or less concrete. So if you have a concrete floor, like middle deck, those are very heavy. We cannot probably get those loads to work. So we say you have to have less concrete, but since you guys are going to be looking at all the sets anyway, these are conversion limits that you should be looking for, and then the other ones just keep it for record, like Tim wants to see how big do we need to go to get those jobs. But to start out, we won't be getting many of those jobs because it's limited in a way. Is the floor composite deck, or does it have 1 inch lightweight concrete or less? If it's yes, then we could go and try to get that set up plan. You have that set up plan already, but then these are mostly for sales guys to get those plans to you. So when you get these, hopefully they'll meet all those criteria. But when you're reviewing the ATS drawings as well, then you at least have some limit to see, should I convert this one or not? Because if you try to take it and convert it, many times you find out our link is just too small. The strength doesn't work, or our beam is too shallow. The deflection doesn't work. So, is the beam clear span 28 foot or less? Yes, then we'll do it. Is the height 24 foot or less? Then yes, then we'll do it. Is it 3 stories or less? If it's yes, then do it. So that's why now they're limiting it to the 3 stories. That number could vary. We don't know what the demand is. All depends on loading. So if you have the less low, then we could potentially go higher. If it's higher low, then the link cannot support it. Then we can't do it. So that first set is a 3-story minimum, a maximum. Was the frame designed as a pin base? A yes or no? If yes, we start. No, we'll have to do a little bit more. I'll go into that a little later when we're doing the base plate design. Is the frame has no beam web connection. Corner. This is what I was telling you. We cannot do corners right now. We only have one direction, not bi-directional. So if they're yes, no beam web connection, then there's a yes. So if it's all yes, then we're directing our salespeople to get a set of plans for their engineer to review. And once the engineer reviews is okay, that's okay, then they will submit it to you guys. So this is what basically out there right now. And if you guys see the plan, if you have the plans already for ATS jobs, you might want to apply the same criteria to see if you could convert it or not. Okay, so custom link worksheet, don't worry about this at this point. This is for intended to if we just sell the link, so they have to fill it in and we'll fabricate it for them. And then 1-story worksheet in the back. So we have the 1-story and 2-story in the catalog. So that's basically the catalog for review for what we're offering. So at least you know what we're offering, what limits we have. So outside of that, we might need your support. 2 types of traditional SMF, a weakened beam or stiffened connection. We show that for all the traditional SMF connect, the beam is used to, for the energy dissipation, plastic hinge form in the beam, and you really can't reuse the beam. Beam bracing is required to prevent beam lateral torsion buckling and form plastic hinge in the beam. Simpson strong frame has a designated fuse, so a plastic hinge do not form in the beam. Since the beam is designed to remain elastic, no beam bracing is required. And that's it. Any questions? And well, you guys are gonna make 3 questions for me. So right now, anything that come up in your mind? If not, I'll put these presentations in the directory, and then you should be able to access all of them. So let me try to stop this.
Do you have